So z is x plus iy. So x and y are real. I square root of minus 1. And f, so we can write it this way, fx plus iy. So in that case, you could think of it, yes?
Could we get some additional light in here? The camera likes a whole bunch of light.
Or
both? Or
both? Okay.
Okay.
All right.
No vampires in here, right?
All right. Because we just don't have enough light coming in through the windows. Yeah. So you can think of it as a function of two variables. So in that sense, it's kind of multivariable, which we're going to exploit in a bit. But the other way we'll write, this is a complex valued function, so we can also write it this way. U of z plus I v of z. So u and v are both real valued functions. So they may take a complex number as input, but they return a real number as output, and then they're assembled. So that f of z takes a complex number in, puts the complex number out. So, what if we want to differentiate this function? You might think it works the same as for differentiating real functions. Yes and no. Apparently, USM does not offer a complex analysis course to undergrads. It's a, I think maybe it's a mixed undergrad-graduate course. But complex calculus or analysis, unlike the real numbers, is full of surprises. So f prime of z, well, you can define it in the same way as for reals. Limit as h goes to 0, f of, so at a specific point z naught plus h minus f of z naught over h. So at first it seems there's nothing different, but there is something very different, and that is h is complex. So it has a real part, it has an imaginary part. So it's kind of like those problems we were looking at the very beginning of the semester, where you had functions of x and y, and you had to see, does the limit have the same value as you go to 0 along any path? So what you did before, you looked at paths like this, like y equals mx, things of that nature, to see if limit did not exist. Well, in the complex case, it's the same idea, where you have your real part, an imaginary part, you have a complex number, u plus iv, which you can also think of as a point, uv, in real two-dimensional space. So however you go to 0, the limit has to be the same. It's exactly the same issue. So, so there's natural identification of stuff we've already been talking about. So let's look at two particular cases. Suppose that h actually is real. Then what you're doing is f prime of z naught, which is the same as f prime of x naught plus I y naught, so we'll break it up and work with real numbers. So that's going to be the limit, as h goes to 0, of f of x naught plus h plus I y naught minus f of x naught plus I y naught over h. So it's only the real part that is changing. It's having its real number h added to it. The imaginary part is staying the same. So you can actually think of this as partial of f with respect to x. So we're differentiating with respect to one of the real variables, the real part, at z naught. So that's what happens if h is a real number. But now suppose h is what's called a purely imaginary number. So same thing, same limit, only now so this h is still going to be a real number, but now we're going to tweak the imaginary part instead of tweaking the real part. We're going to tweak y. So now we have I, y naught plus h, minus f of x naught plus I y naught, over IH. So what happens here is you get 1 over I partial f with respect to y at z naught. But that's the same as saying minus I partial f with respect to y. So that's what happens if you compute the limit along this path instead of this path. So depending on how much path you choose, you always get a different value. Except we need these. That's a really long equal sign. These have to match in order for the derivative to exist. So let's suppose then if it does exist, what does that mean? Well, for that, we're going to break f up into u and v. So
how is it that 1 over I is equal to negative I?
Yes, it is kind of weird.
You do the conjugate? You multiply by square root of negative 1?
Well, it works like this. In a complex plane, if you look at the unit circle, so this is the real number 1, real number minus 1, so this is the real number line. Here we have I, is up here, because you can think of the real part as being x and the imaginary part as being y.
All right.
So I is up here, minus I is down here. So what happens is I to the 0 is 1, because anything to the 0 power is 1, that's still true. I to the first is I squared is minus 1, I cubed is minus I to the fourth brings you back to 1. So exponentiation is taking you around a circle.
Okay.
So I to the minus 1, so now you're going the other way. The cycle holds for negative exponents too.
Okay.
Yeah. It's kind of strange, but...
So if you do like I to the 1.5, then that's valid, or?
Yeah, I to the 1.5 would put you over here. So each power takes you 1/4 of the way around the circle. So this is I to the 3/2. This is I to the 1/2, and so on.
Well, that was interesting.
Well, just you wait. Now, so if these are to be the same, I forgot that this yellow chalk is not so good for erasing. So that means that partial of f with respect to x, which is a partial of u with respect to x, plus I partial of v with respect to x, must equal, right over here, minus I partial with respect to y, which is minus I partial of u with respect to y, plus I partial of v with respect to y. So these have to match. So now, that means this is equal to minus I partial of u with respect to y. And then here we have minus I times I, that's I cubed times I, that's I to the fourth, which is 1. So we get plus partial of v with respect to y. So these two have to be equal. But all of these partial derivatives, they're all real. So you have to match real parts to one another, imaginary parts to one another.